lecture, JEOL 2100 plus 200 kV. Basically, when we talking about TEM, then we say accelerating voltage. Reference is accelerating voltage. 80 kV. Sometimes are 80 kV. Their voltage is not 80, 120 kV. In that 80, 100 and 120 kV is there. That is meant for biological sample. One time that is normal time. We have also that not working right now, but that was up to 120. Then advanced next version that comes to 200 kV. Means kV means kilovolt accelerating voltage it is generating from top. Smaller wavelength it is generating means higher the accelerating voltage means smaller wavelength, finer resolution. And again, as I told, cost is going to add. After 200 kV and again filament, we are talk about filament. Just like we have purchased electric bulb, simple bulb, tungsten 12 rupees, 15 rupees, CFL or other type of fluorescent and bulb that cost in hundreds. So same tungsten bulb filament is there, its cost is around maybe 1 crore of TEM, 120 kV. When we say this have LABCs, lanthanum hexaboride filament, it cost is around 4 crore, 200 kV. If we same system we go for 200 kV field emission, just like we have field emission SAM, same field emission TEM will also come. Field emission TEM we go to 100 kV at field emission it cost maybe 15 crore, like that, completely will vary. 200 kV then we can go to 300 kV field emission. Again we are talking of that wavelength. Wavelength going in suppose 5 picometer to 1 picometer. Coming from 5 to 1 picometer of angstrom, 5 angstrom to 1 angstrom, that cost and the resolution, quality, everything is going to change that drastically. We cannot imagine. Again, sample quality as per quality of sample. So this is the overview of things, but the rest machine in all case is same. Fundamental principle is same, everything is same. Layout wise, many times you find some bigger. If you need 300 kV field emission or 200 kV, it's something bigger diameter because it needs some more isolation from external environment. It don't need much vibrations because when we are going to do high resolution image, that thing is going to you can say dislocate, disresonate, because when we tap strongly or movement or outside more movement, it's going to disturb in case of high resolution image. So due to that things are going to you can say broad in case of 300 kV or bigger TEM. Layout wise, at the top we have electron gun. Basically, it is a reverse of light microscopy. If you talk of first you need to understand light microscopy, then the concept of electron microscopy came. If you go in the history, right? At that time, resolution was a challenge because they are going to see through visible light. They are not able to see in much depth. So that's why at the time concept of electron source in place of light come. They have done a lot of things. It will take many years, and from 1935. It will take 1982 to get the Nobel Prize in this. So things have taken the time. Right now, keep on moving away. If you go in 2017, Nobel Prize for the protein structure was given by the cryo-TEM. Cryo-TEM is again one more category, which means for biological sample under stabilized condition. That is separate instrument. So layout-wise, electron gun is there. As we are going to deal with electrons, so we need condenser lens. But again, condenser lens is also light microscope, but that is just to control the light. Here we need to control the electron beam, so we need electromagnetic lens. Electromagnetic lens arrangement is there, like coiling is there. And this from inside is not big much, it's just like that hollow column. In that vacuum is there, right? Condenser lenses are there, movable condenser aperture. As I told in diagram that something is to be removed by putting some strip like thing. It is like some diameter, light is passing through diameter. Suppose beam is coming like this, so it passing through narrow diameter, extra will come as stray, loss in the form of heat, only a fine beam will pass, right? This is the purpose of this aperture, and you can see we have different diameter of aperture. As I show in one presentation, 10 micrometer diameter, something like they have shown. So there are different diameters. Suppose 20 micrometer, 10, 5, 2, like that. Smaller the diameter, smaller the beam we can generate, right? So beam just like coming like this, it becomes small. But in which
for the
contrast, or you can say suppose you have very strong sample, some material science sample, some semiconductor, so you need more penetration to elaborate. But again, if you have some biological sample, we need not to put it stress. So we many times make the broad beam, not without aperture, because that have bulk illumination, so it will burn the sample. So it's a live things we need to do. This is condenser aperture. This is a sample stage. here we are going to insert the sample. Right now sample is inside the machine, right? So just like नहीं ऐसे में निकालना है बस बाहर ही लेना है. Right now we have moved the sample somewhere, so now I am putting it to the home. That stage is going to home. It was somewhere because we have searched something. Now bring it to 0 position, x, y, z, 0, 0, 0. Stage is here. Now I am taking it out. Here you can see this is an outline. You can see your specimen chamber is ready. This is specimen chamber. I am taking the sample holder out. I need to push it as it is in vacuum. So yeah. And I have make it come to air. As suddenly you can see it was from ready to not ready. In that part things get. Rahul ji,
Okay.
silver nanoparticle. So just right now I have taken holder out. Just for the demonstration I will show you.
Okay.
So can I insert the holder?
Yes.
In the
Pumping.
not without fixing right now in the air.
Okay.
I will insert.
You need to pump.
Pumping.
Pumping कर.
Pumping. Now this atmosphere. Then push here. Then switch on. Then start the pumping. Yes. Then after green and turn on, we can just a pre-pumping. Pre-pumping.
You can sit second.
Because inside the car, then install the sample, pre-pumping and vacuum level better, then install.
Which sample is it?
Now,
Silver nanoparticle.
now 200 kV apply already. Then behind that box is a high voltage generator. High voltage generator. 200 kV DC high voltage.
Hypothesis.
And right hand box is a power supply. And also the top of the column is the emitter, an accelerating tube, and condenser lens system, objective lens. The sample install center of the objective lens. The intermediate lens system, projector lens system, final image comes to screen. Then we can observe the screen. These are stem detector, scanning detector. Then these are aperture, condenser aperture, objective aperture, selected area aperture. And this is the liquid nitrogen tank. Inside of the objective lens, very close to the specimen chamber, there are small metal fin. The cooling down is the fin with the liquid nitrogen. Because some is a kind
Yes, this one.
the sample is among the then position changing as like this. Then switch the This is not silver part, no? It's small. It's very small part there. Just looking for the some other particles. very small. Now this is now
200.
Then
200.
just increase the magnification like this then. Silver particle. Just intense increase. Magnification now 50.
60.
60, 60,000 times magnification. Then particle diameter very small as a scale.
Is around
200 multi 39.
This much is 200.
Yes.
You can observe
Okay,
how much
just
the
check.
particle size is. Almost around 10 to 20 nanometer.
Just around.
Thank you.
And good focus is a wobbler. Then vibration. Then adjust the standard. Like tight adjustment. Like this. Okay. Then you can see here some of the diffraction contrast. Hi. Ghost appear. This is a diffraction contrast. This is a crystal. Then we can magnify, we can observe the crystal lattice. Just try. Increase the magnification. Like this. Here. Then this is the crystal, silver crystal. Then focus adjust. Hi. Magnify. Now 400,000 times
Yes.
magnification. Very high magnification. Maybe you can observe the lattice.
Yes. That
Maybe here the lattice. It's a silver particle. Maybe it's a very small particle. The scale marker is 20 nanometer. Maybe diameter less than 10 nanometer. Very small. One more higher magnification. Here.